Thermophysical properties of CO₂. The behavior of a refrigerant within a vapor compression system is governed by the thermophysical properties. CO₂ differs significantly from conventional synthetic refrigerants, and these differences strongly influence system design and operation. Figure 1 is a phase diagram for CO₂ at temperatures from -80°C to 80°C. The diagram is divided into regions representing solid, liquid, gas, and supercritical states, separated by phase boundaries where transitions occur. Overall, the diagram illustrates that the state of CO₂ depends on both temperature and pressure, and highlights the absence of a liquid phase at low pressures and the emergence of supercritical behavior at higher temperatures and pressures. One of the most important characteristics of CO₂ is its low critical temperature of approximately 31 degrees C, combined with a critical pressure of about 73.8 bar. In many heat pump applications, the temperature at which heat must be rejected exceeds this critical temperature. When this occurs, the refrigerant cannot condense regardless of pressure. Instead of operating as a conventional subcritical cycle with condensation, the system operates in a transcritical cycle. The critical point is the highest temperature and pressure at which a pure material can exist in vapor-liquid equilibrium. In transcritical operation, the high-pressure heat rejection process occurs above the critical point. Rather than condensing, the refrigerant passes through a gas cooler, where it remains in a supercritical state and cools sensibly. During this process, the refrigerant temperature decreases continuously rather than remaining constant as it would during condensation. This produces a temperature glide along the heat exchanger. The glide allows the refrigerant temperature profile to more closely match the temperature rise of the water being heated, reducing temperature differences and improving heat transfer effectiveness. Several additional thermophysical characteristics reinforce these advantages. CO₂ has a high vapor density and volumetric heating capacity. This enables the same heating capacity to be achieved with smaller compressors and significantly reduced pipe diameters, which could be advantageous in plant rooms where space is constrained. The refrigerant also exhibits low viscosity and high thermal conductivity, resulting in high heat transfer coefficients and allowing heat exchangers to be relatively compact. Other important characteristics is the triple point of CO₂, occurring at approximately -56.6 degrees C and 5.2 bar. If pressures falls below this level, CO₂ can solidify into dry ice. System safety design must therefore ensure that pressure relief and venting arrangements prevent conditions that could allow solid CO₂ to form and block discharge paths, particularly during rapid depressurization or maintenance conditions. While these properties create engineering challenges, they also enable a distinctive heat rejection process that is well suited to high temperature heating applications.